And welcome to another week of .NET Entertainment with on .NET Live. We are unscripted, especially right now because I'm realizing that I forgot to bring up the script for the intro. I'm here with my co-hosts. I'm Cam Soper, and I'm here with my co-hosts Cecil Phillip, returning from a hiatus, and Myra Wenzel. And this week's guest, Aaron Stannard. Aaron, can you tell us a bit about yourself, please?
Well, absolutely. So my name is Aaron Stannard. I'm one of the creators of the Akka.NET project, and I'm the founder of Petabridge, which is a company that provides training, support, consulting, and some paid add-ons for Akka.NET. So we're a commercial open source business. And aside from that, I founded another company kind of in the .NET space called Marked Up Analytics that did real-time marketing automation analytics for apps that are running in the Windows Store. And prior to that, I actually worked as a developer evangelist for Microsoft back in 2010 to 2012. I was on the field team for the BizSpark program, if you are familiar with that back in the day. But yeah, that's me. And I think today we're going to talk a bit about Akka.NET and distributed systems in .NET.
That's awesome. And you're also pretty heavily involved with the .NET Foundation. Is that right?
That's right. Well, the Akka.NET's a .NET Foundation project. And so, we've been in it for, I don't know, probably 5 years now, just about, maybe 4.5. So we've been in the foundation for a while. So I'm basically in it largely as a project lead. And, I'm obviously pretty vested in sort of the health of the .NET open source community. I mean, it's literally my business. So I do have a lot of skin in the game there. And it's something that I'm just generally speaking very passionate about. I think what open source really lets developers do by and large is have the freedom to experiment with new ways of trying to deliver software without having to go through the procurement department first, which is the bane of basically, if you're trying to sell products to software developers, the procurement department is where dreams go to die, more or less. um,
Well,
and
I was
go
just
ahead,
going to say,
sorry.
apropos of that, why don't we jump into our we actually have a little bit about the .NET Foundation for our related bits segment.
All right. Yeah. And so thank you for the nice intro there, Aaron. And so our related bits today, it's the .NET Foundation website. And so you can visit at dotnetfoundation.org and you can find information about how you can join as a member, how you can onboard your project to the .NET Foundation. And you can find a lot of resources for the community as well. We have like workshops, we have meetups, and a lot of materials for you to build that knowledge and build that community sense with .NET. And so there's tons of things here. And so go check it out. I like how Aaron introduced the part of onboarding and procurement and make it easier for projects to ship and deploy, right? Am I
Cam, I
having?
think you're muted. We can't hear you.
I am muted. Sorry about
Okay,
that.
I was like,
So
am I
no,
having
no, no.
audio
So
issues
forgot
now?
the script. Forgot the mute button. Yeah, it's Monday. So with that, why don't we jump into our hallway track so Aaron can show us a great .NET Foundation project. All right, Aaron. The floor is yours, sir.
All right. Well, I know since as a former Microsoft employee, I know how much we all love PowerPoint.
Oh my gosh.
So you can't get enough of it, right? So also, in order to be on brand, I'm actually recycling my PowerPoint presentation from .NET Conf 2019. I figured, you guys would appreciate that.
I think reuse is important. It's important that we reuse, software. So
well, it's in the spirit of open source.
Exactly.
It's in the spirit of open source, and also this information's timeless. So I figured it'd be worth talking about. Well, I'm not going to bother going into full presenter mode here since we're keeping it casual. I'm just going to go ahead and kind of click through my slides. I figure that'll be a lot more entertaining than me giving a canned speech here. But the gist of it is that Akka.NET's an implementation of a very old idea in computer science, the actor model. And that's really kind of its foundation, and its role in the .NET ecosystem is a canonical implementation of the original sort of Erlang style actor model in .NET. And before I get into the details of Akka.NET, kind of want to talk a little bit about what are actors. I've given some talks before and put some literature out there about the origins of the actor model. In fact, if I jump to the end of the slide, these are the slides I did not include in my original .NET Conf presentation because I think that was like a 25-minute long talk. The actor model stems from back in the 1970s. So just to kind of set the context of how old an idea the actor model is, the original actor model white paper was released about 2 years after the original relational database white paper was. So they're pretty close together conceptually in terms of age. The difference is, though, is that the actor model in its time and place was designed to be a way to build concurrent distributed systems that were going to run in these gigantic warehouse-sized cathode ray tube computers, where you can go ahead and imagine, a machine that had hundreds of thousands of cores would take up, 12,000 square feet of space or something like that. Just say an absolutely gargantuan computer. And they needed the ability to reason about a cooperative programming model that would allow some work to be distributed to some cores and to send the results back to others and allow this sort of inter-process communication to succeed. Concepts that we take for granted today, like threading and multi-process architectures, were not really discussed back then. Those came a little bit later in the 1980s for the most part. So the actor model was this concept that was originally developed for being able to kind of reason about inter-process, like large-scale concurrency in the cathode ray tube mainframe era. Well, the technology that ultimately eliminated the need for the actor model was the silicon conductor. It greatly reduced the size of the computer. Moore's law took over, and every 18 months, we got double the amount of throughput that we did before. There was no need to have this, let's say, actor-based implementation where the way the actor model worked, in essence, just kind of showing you how it was originally conceived in the 70s, was you would have a program. In fact, let's see if I can make this a little bigger. There we go. You would have a program that would kind of run on like a foreground process here, and it would spawn child processes, essentially. Each actor was kind of its own microprocess with a discrete life cycle, its own private memory, and its own ownership over a single core in this model. So this program would distribute work via in-memory message passing. It would distribute messages via a shared memory bus to all of the different processes that were all cooperating inside the same machine. So you'd basically have this kind of fork join model where the work would be distributed and spawned into these actors. They would all complete their work independently and then send the results back. And this had a complex animation on it that I'm not going to go through. But long story short, all of the results would be gathered back into the main program eventually and coalesced into some sort of intelligible report. Now, this introduced a whole bunch of novel ideas back at the time. The introduction of actors, the idea of message passing as a first-party sort of inter-process communication construct and so forth. But like I mentioned, Moore's law more or less eliminated the need for this back in the 70s. What brought the actor model back into resurgence was really the creation of the internet. Erlang, which is probably the first canonical implementation of the actor model in market, is short for Ericsson language. It was developed by Ericsson when they were building the first digital telephony exchanges in about the mid-1980s, around 84, 85 is when they were starting on that. And they needed to have a highly fault-tolerant, low-latency way of being able to route voice and data packets over, basically between subscribers on the network. The other thing they really needed was the ability to achieve what's called horizontal scalability, meaning that if I double the number of subscribers on my cellular network in a large city like New York, I need to have a predictable way of knowing how much more hardware do I need to provision to service those customers. If I don't have that, if my system has, let's say, a shared bottleneck somewhere, then that means that we are going to be limiting the growth of our network via some sort of software constraint. And that's ultimately going to damage the business, and it's going to hurt the quality experience for customers. So we need to have a way to achieve horizontal scalability, and really linear scalability is the goal there, where if I double the number of nodes, I double the throughput. Turns out the actor model is a very efficient way at achieving that because it lends itself very well to decentralization, meaning that all of the business intelligence and all the decision-making is pushed out to the edges of the network inside the application itself, rather than being centralized in a single location like a database or an enterprise message bus or something. And so the actor model was a perfect fit for this. And so originally it was developed to serve these sort of telecom networks. But eventually the other places were, after Ericsson open sourced Erlang, I think in the early 90s is when they did that, like 91, 92, somewhere in there. The first real major adopters of it in the age of the internet and the World Wide Web were people building some of the first low latency applications like advertising exchanges or multiplayer games. And then eventually it started stemming into real-time communications apps. Probably the most famous adopter of Erlang I can think of is WhatsApp, runs on top of it, for instance. So Erlang is still quite in use today. It's definitely been revitalized through technologies such as Elixir, for instance. Elixir. Sorry, I had a bit of a brain fart there. It's still basically very much in use today, and the Erlang community is still very active. But something that developers wanted as the cloud kind of drove the need for this sort of actor style of programming to become more commonplace, and I'll talk about what those factors were in a second, is people wanted access to the actor programming model on generic runtimes, meaning Erlang has its own specialized virtual machine and its own specialized language and interpreter. And by the Erlang, the syntax itself is like pretty gnarly, to be honest. So people wanted access to the actor programming paradigm through general purpose virtual machines, such as the common language runtime that powers .NET, or the Java virtual machine that powers the JVM ecosystem. And so that's where Akka, the sort of original canonical like JVM implementation of their actor model came from. And then Akka.NET is a port of that to the .NET runtime.
Aaron, let me jump in real quick.
Yeah.
I have a couple of questions. First of all, I have a question for me. So a lot of what you describe in that actor model, and by the way, this is my really first exposure to the actor model. I've messed around a little with Orleans a little bit, but not like in depth. How is this similar to like a microservices architecture?
So it's similar to a microservices architecture in the sense that you take, let's say, a responsibility inside your application and you encapsulate it inside its own actor type. And then you create multiple parallel instances of that actor type in order to go ahead and either guarantee mutual exclusion. So a good example, if you have an actor that represents a domain entity inside your system, and so an example of that from one of our customers might be keeping track of a device, doing digital twins or something like that. You might go ahead and have, let's say, so we have a lot of customers in the energy industry, for instance. You might have one actor represent one power meter connected to one home, and you're processing, you know, at a set interval these little UDP data packets that show what the most current meter reading is, right? So you might go ahead and distribute millions of instances of those. Where the actor model and microservices are similar is that idea of, let's say, distribution and encapsulation. What's different about it is how granular the scope of work is, and location transparency is what's really different. So actors scale down to much smaller units of work than a microservice does.
Okay.
That's probably the first sort of, let's say, conceptual shift there. The others is location transparency. You can have millions of actors that are all have their discrete data, have their own unique address and everything else, all running inside the same process. Or they can be spread out across hundreds of processes. The great part about the actor model is you don't need, as the programmer, to explicitly know or care which is which. Now, there are some performance implications for certain types of applications that will force you to care. A good example of that would be something like graph search. If you want to perform very low latency graph searches with a technology like Akka.NET, you want to make sure all the nodes in your graph are all local to each other in the same process. That way, there's no serialization or network I/O involved in doing that. And that's fairly easy to control in Akka.NET. I'll get into some details on that. But that's sort of the first. That's sort of the first, I guess, sets of differences and similarities between actors and microservices.
Okay. Well, I was wondering because a lot of that sounded pretty familiar because I've done a lot in the microservices area. So now we have a few questions. Actually, they're all from one of our frequent viewers who asks some of the best questions, actually, Jose. The first question he asked was, why, you know, what's the advantage in using actors as opposed to using threads when...
So the first advantage of using actors is they are a resource that uses no computational time whatsoever when they're not busy. Meaning that if you create a million actors and then you only schedule, let's say, a very small percentage of them to process any messages at any given time, the other actors that are idle don't consume any CPU whatsoever. So and the reason why that is the way Akka.NET's infrastructure works is that there's a dispatcher, which is essentially the .NET thread pool, is what it really is. There's a dispatcher that's responsible for performing scheduling and execution of actors. That dispatcher can basically line up several thousand actors to all go ahead and process messages in a very short window of time. An Akka.NET actor will process in the ballpark. Actually, we just improved it with .NET, with Akka.NET 1.5 quite a bit. We took advantage of one of the new .NET APIs that was added in, I think, .NET Core 3. But actors can process in the ballpark of about 5 to 6 million messages per second. And most of that, the reason why that value is not even higher is because of what's called the quantum we use for scheduling actors over and over again. We only let actors process a burst of about 30 messages before they have to yield and give another actor a chance to process. This is what allows multiple actors to process work concurrently in an environment where maybe you only have a single core, which happens more often than you'd think. Akka.NET can run on embedded devices like mobile phones or sensors that are embedded in the field or very small computers like Raspberry Pi. And people do this quite often with Akka.NET. So that's one set of advantages is basically the fact that there are cheaper resources that require less management. The other is that it makes the ability to go ahead and schedule when work happens very arbitrary and easy, versus with threads, you basically have to kind of manually synchronize things. You have to manage work queues for them individually. And on top of it, you still have to deal with essentially the thread lifecycle management. What do you do with a thread when it has no work? You have to come up with an algorithm for either causing the thread to spin, which can utilize a lot of CPU in the background, or you have to put it to sleep, which can increase latency. With AkkaNET actors, you don't really have either of those problems because they're going to use one of the available threads in the .NET thread pool to work right away.
So, so Jose's next question, which builds on that, and I think I already know the answer to this. So, is Akka.NET thread safe?
Oh, 100%. So I haven't gotten into conceptually kind of like why the actor model is attractive in the modern day and age, but its primary business value from, let's say, the point of, so there's the whole distributed systems part of Akka.NET, which is building large scale cloud systems. Let's set that aside for a minute. If you talk about Akka.NET in the terms of a local process, so a good example, Myra, you were just talking about building Maui apps a minute ago. Akka.NET gets used in quite a few WPF and Xamarin applications, which are, by their very nature, they're not distributed. There are local clients running on a single user's computer. What actors are really powerful at doing is they radically simplify thread safety. And the reason why is that all actors are serial processors, meaning that actors can only process one message at a time. They basically operate on a message loop is the way to think about it. So when you put messages into an actor's queue, that queue is what synchronizes the actor message order. It's basically a concurrent queue is what it is. Actors get scheduled to process those messages in the original order in which they arrived, which means that all of the data that is held by that actor internally is guaranteed to be thread safe. The one thing an actor must do to help guarantee that thread safety across many different actors that are running in parallel is to make sure your messages are designed to be immutable. So that means using records in C#. In F#, you get immutability by default. But those are basically that's all you really need to do in order to guarantee thread safety inside actors. And it's one of the reasons why people look at using it even inside things like desktop applications.
Okay. Well, I think we can come back to more questions later. I think the audience is dying to hear more about how Akka.NET implements the actor pattern.
Sure. So I'll go ahead and dive in. Oh, sorry, go
And
ahead.
someone asked to do the full screen of the presentation to read
okay.
better. So if you can do that, if it's not.
Sure thing. Let me, how's that look?
Yeah.
Sorry about it. I was trying to be cool and casual.
Yeah, but someone was saying it was hard to read, so let's adapt to it. And
we definitely got it. We definitely got to take care of readability. Absolutely. So installing Akka.NET, in terms of if you want to go ahead and play around with Akka.NET, what do you actually need to do it? Well, to run actors locally inside your Xamarin app or inside Maui application, all you need is the core Akka package to do that. And Akka doesn't take any dependencies on anything else. In terms of, let's say, you don't need a database to run Akka.NET. You don't need a network. This will just give you the ability to create an actor system, which is kind of the shared namespace for actors. And then it gives you the ability to go and spawn individual actors. If you want to go ahead and have actors work across processes, we have Akka.Remote, which enables that. If you want to make actors durable, meaning that actor state gets event sourced to a database that can be recovered when an actor restarts or is killed and moved to a new process, you can go ahead and use Akka.Persistence for that. And then we have Akka.Cluster, which is what I'm going to be doing my little demo of with Azure Kubernetes Service, is all Akka.Cluster. This is how you build those Erlang-style networks that are highly available and linearly scalable and highly fault-tolerant and all that good stuff. That's what Akka.Cluster is for. Now, in terms of what an actor actually looks like, here's the source code for a really basic Akka.NET actor, where we create a class and we inherit from this receive actor base class in Akka.NET. And what we need to do to actually program this actor is we have to go ahead and create some internal state. So in this case, my only piece of state is my logging adapter here. This is sort of the asynchronous interface actors use for writing logs out to the log system. And then we have down here our receive methods, where in this case, I'm going to say, if I receive a message of type ping, I will handle it using this method. And so when we talk about actors only processing one message at a time, here's what we mean. If I have multiple receives defined for multiple message types, and I have multiple instances of this message in my mailbox, I can only process a maximum of one message of any type at any given time. And until this actor exits its current receive message method, it can't begin processing the next message in its mailbox. So that's what we mean when we're talking about basic serial message processing inside Akka.NET. Now down here, when we receive this ping message, you'll notice we have this property called a sender. A sender gives us what's called a reference to another actor, an actor reference. That's the little handle we can use to send a reply message back if we want to. And in this case, I am sending a reply back, but I'm using the scheduler to delay it 5 seconds in the future, which is not normally how I would do it, but because this is just the way I wrote the sample, that's what we have here. If I go and pull up one of my other code samples here, let me grab this one. This is my large Akka cluster sample we'll take a look at a little bit later, but I have down here a ready check actor. This actor actually responds to a Kubernetes health check sent via an HTTP API that I have. And we just have to go ahead and reply back. Are we currently in a cluster right now? And is the cluster trying to shut down? And basically, if this is true and this is false, then it means that the cluster is healthy. And I go ahead and I reply back to the sender with a new message, this ready result message right here. And this is an immutable class as well. Even though it's not a record, it's because it's read-only is what makes it immutable. So I go ahead and I reply back, and that message gets processed by an HTTP controller, which returns a HTTP 200 if I have a Boolean that returns true, and it will return, I think, a 500 or maybe a 400. I can't remember exactly if my readiness check fails. So that's kind of the basics of what an Akka.NET actor is. So as you can tell, they're not very big classes. They're pretty simple for the most part. I'm going to go back to my PowerPoint here. Here we go. Good. I was hoping this was the next slide. I just couldn't remember without looking at my outliner. So the way we go and create actors is we have to create what's called an actor system first. Every single member of an Akka.NET cluster is really an actor system. So when we talk about nodes in a cluster, we're really referring to actor systems here. Each actor system is basically an address space for creating actors. And in order to start an actor, we have to first create props for that actor here. So this little code right here, props.create, this is basically a recipe for how to start this actor is what it is. This doesn't actually invoke any code on its own. We're actually using the expression compiler to extract the actor type, the constructor arguments, and which constructor method we need to use. That's really what this is doing right here. And then when we call actor system.actorOf, this is what actually creates an instance of this actor with this name, and it returns an actor reference back to us. And that actor reference is what we can use to send a message. Now, I'm a little embarrassed to mention this, but it took me like 4 years to figure out that this is called props because actors in real life use props in order to act. I thought this was short for properties the whole time. So I totally didn't get the analogy there for years. But basically, this is kind of the basics of how you go about starting and creating actors right here. And so when I tell that actor you saw on the previous slide, this ping message, this is what will cause that actor to go ahead and execute it and run, is when I tell it this message this way. Now, one thing I should point out is that the tell method is void. It doesn't return a task you can wait on, but it's still asynchronous. The reason why is that the tell method exits only when that message has been queued into the actor's mailbox. We don't actually get a notification back that that message has been successfully processed, and that's by design. One of the things Akka.NET's designed to help guarantee is very high throughput and high performance. One of the ways we go about doing that is encouraging non-blocking workflows. Fire and forget messaging being one of them here. That's one of the defaults. Now, we do have another way of interfacing with actors where you will get a notification back when the actor's completed the message, and I'll get to that a little bit later. Any questions so far? Should I keep going?
Yeah, I have a quick question I wanted to ask you. So I know you've shown like how to create the actor system, how to create actors. And you've talked a little bit about like the role they kind of play when you think about processing work in comparison to things like threads and those types of things. So if I'm a new developer to the actor model and I'm trying to figure out like what part of my application does this sit in, right? Can I say, okay, I'm building an app and this is almost like the service layer of my application, right? Like, so, you know, when folks do like those layered types of architectures and there's a UI and there's a service and there's a database thing at the bottom. Can I think about actors or particularly Akka.NET as the okay, hey, I want to process some work, right? Like a request is coming from my API or someone clicked a button. Now this is the thing where the actual work happens, and I send it out into the actor system. It gets queued up, some work happens, and it comes back, right? So is that kind of where we think about it?
Yeah. So, this makes me think. Let's take a step back from the syntax for a second and talk a little bit about the role that actors play in modeling a system here. So let me see if I have this one up and running behind the scenes. Looks like I do. Great. I have a little SQL Server instance running behind the scenes here. And let me go ahead and fire up this AkkaNET application. This is more of it has a very minimal domain, but at least it has one, whereas the other samples are just kind of free-floating syntax. So let me pull this up real quick, and maybe I can help talk through the role actors play in the domain in someone's application. Like what part of, because your question, if I understood it correctly, Cecil, is kind of, if you think about my application layers, where does Akka.NET really fit in the grand scheme of things?
Yeah, exactly.
Okay. And the answer, very annoyingly, is that it depends, depending on what it is you need to accomplish. And I'm going to go ahead and fire up this. This is a application that is in one of our shared public repositories. Let me go ahead and grab a link to it in just a second. I'm just waiting for good old IIS to fire up here. Here we go. All right, perfect. So this application, in fact, I've got another browser tab open that has it right here. This application is, if you go to the petabridge/Akka.NET code samples on GitHub, this is our cluster sharding with Akka.NET persistent SQL Server and Razor Pages sample. And that's basically what I'm running here. So I'll drop a link to this in StreamYard if you want to share it with your audience. And the basic gist of this sample, if I go back to my UI here, is I have the ability to create products. And this is all being powered, by the way, with actors behind the scenes. So I'll walk through some of the source code in a minute. But I have the ability to go ahead and create products. I'm a bourbon aficionado, so I've been creating various Buffalo Trace bourbons up here. So I'll go ahead and add another one. Yeah, I'll go ahead and do, tell you what, we'll go and add a new product. We'll do Weller Antique 107. We'll go ahead and price this. I think its MSRP is $35. And we'll say there's 1,000 of them available behind the scenes. All right, great. Looks like that's now available. And if I go back home, we can go ahead and see Weller Antique now appears on this list here. So how am I actually using actors inside the system at all? Well, I'm not using actors to power my UI. If I take a look at this code sample, is the font size good, by the way? Is this pretty readable for everybody? Or maybe I should go a little bit bigger.
I'd say bump it up like 1 or 2 more points. Yeah.
That's what I was going to say.
All right, cool. So if we take a look at my application here, I've got 2 different processes. This is a little distributed system that I've built. But the actor that's basically doing all of the work is this product totals actor right here. Well, this actor has a unique identity, and this unique identity is associated with the product that we're creating. I believe the unique ID is just a GUID I'm generating from scratch. That ID could be a natural key, or it could be something you pull from a database like an auto-incrementing ID if you wanted to. And what I'm doing is this actor receives commands. And in response to these commands, it'll produce, this is basically a sort of an event-driven architecture is what I have here. So I have these product commands. And if I go to definition, let's see, go to implementation here, you'll see I have commands like create product, purchase product, and supply product if I want to. The role that actors would fulfill, let's say an e-commerce scenario like this, would be if you had lots of different components in your system that need to listen for these events that belong to a specific SKU or a specific product inside your system. So a good example, if I go to my UI here and I go to this Weller Antique product I created and I see that there's 1,000 available units, and let's say I get an order for 500, I place that. So I can see that we're down to 500 available units. And then let's say someone orders 600 units. Well, now I'm on back order to the tune of, and I should probably display that here, to the tune of about 100 units. there's going to be some part of my fulfillment system at my company that's going to need a notification about when a new supply arrives. If I go ahead and resupply to the tune of 100 orders here, now we're going to be at break even once again. We've basically been able to go ahead and meet the available all the available orders so far. So if I basically have multiple parts of my system that need to react to these events that are coming in, that's a really good fit for the actor model. If I have, let's say, customers that want to receive email notifications about new product shipments arriving, if I have parts of my fulfillment team that want to know about products arriving so they can fulfill back orders, or if I have, let's say, low inventory warnings I want to be able to issue as a result of, let's say, the number of purchases basically really closely approaching the number of available inventory, I want to have a chance to react to that. I don't want to have to wait for a nightly batch process to tell me about the problem, a day or 2 days after it happens, right? That's kind of the Web 1.0 way of thinking about a lot of this stuff, is this sort of nightly batch routine. AkkaNet's meant to build these sort of real-time reactive processes. And that's really how it's used on both local scenarios, such as running inside a client or running inside the cloud. So to answer your question, Cecil, AkkaNet can be used in the UI layer, it can be used in the business layer, or it can be used in the persistence layer. So for instance, I'm really using AkkaNet for both the business and the persistence layer here. I'm using AkkaNet persistence to store all my state. This index that I'm building on the home page is using AkkaNet persistence query. It's using CQRS essentially to go ahead and create a projection of all the events that are being saved. And then I'm also using AkkaNet to process the business rules around back ordering and that type of thing. Sorry, go ahead, Cecil.
No, I was gonna say, yeah, that makes sense.
So for like a UI example, let's say I was building a real-time chat application. I might have AkkaNet actors manage the SignalR backplane. That's something that they could do very easily. That'd be an example of where they're functioning more like a presentation layer at Facet from that point of view. So the right way to really think about actors is they're a bit of a Swiss Army knife that can be used in whatever area you feel is appropriate. Now, that doesn't mean you should use them in every area for every application. I certainly wouldn't build a CRUD system using AkkaNet actors if there was no reason to do it. Like building a blog engine using AkkaNet actors wouldn't be something I would consider doing because unless I have a need for real-time notifications to go out somewhere, and frankly, I don't think blogging is that important, sorry to say, I probably wouldn't go about building it. Now, building things like in a very large e-commerce system, being able to keep track of notifications and doing event-driven architectures, or maybe you're doing more sophisticated things like dynamic pricing, where you're repricing items as inventory drops in order to try to basically extract as much money as possible. There's a lot of industries that use AkkaNet for that purpose, air travel being a really good example of that. But basically, this is an example that's a little bit more sophisticated than just pure CRUD. It's actually quite event-driven, and the flow in which events arrive into the system are going to have effects, and the actors are used to model those. And that's really what the actor model is all about, is being able to go ahead and propagate those effects in as low latency a fashion as possible. So on the extreme end, in terms of what are the really cool business applications of AkkaNet, some of the ones that we've featured in our AkkaNet community stand-ups recently, these are the meetups we do for the AkkaNet project once a month. We just did one a couple weeks ago from a big biochemical company in Europe. They basically produce things like, pesticides and other products for basically helping produce crops. They were able to, during COVID, automate their entire lab using AkkaNet, basically, where they're automating like long-running organic chemistry experiments, where they have one actor that's operating, let's say, a little valve that might dispense some chemical in there, another actor that's listening to maybe a spectrometer, maybe another one that's running a pressure sensor, maybe another one that's actually photographing a sample over fixed intervals. Then you have other actors that are reacting to those events and are using them to actually produce chemistry readings for these chemists that are all taking a look at it. That's an example of a very small scale application. That's all running in one process. You don't really need a big distributed system for that, just because these are not these are individual labs, right? They're not a gigantic array of 12,000 of them all running at the same time. But that's an example of like a low latency application that can happen even in just a local environment where you need the ability to do things like open and close a valve within 20 milliseconds. Akka.NET can do that. More, let's say, cloud-facing examples of where you might need something like Akka.NET. I mentioned a couple e-commerce ones, but we've also got a lot of customers in industries like sports betting, for instance, where they're using Akka.NET to do real-time odds calculation based on how betting markets are performing. You also have things like people who are running, let's say, foreign currency trading. So we've got a lot of European banks that use Akka.NET to do real-time trading in order to maintain their currency reserves. Now, if you're running a bank in Europe, you might need to maintain reserves in 4 or 5 different currencies, depending on what you're regulated to do. And then on top of that, there's also lots of scenarios for IoT. That's probably our fastest growing market segment, is people doing digital twins. We have a lot of customers in energy, transportation, medicine, and lots of other miscellaneous stuff. In particular, manufacturing has actually been a big one recently. Yeah.
All right. So I have one more question I wanted to ask you. And it kind of goes back to something you had mentioned a little while ago about the persistence. And I'm always curious about how persistence works with actors. Because in my head now, you have a system with hundreds and millions of like these little, these things in memory that are each maintaining their own state. What happens when I get to a point where I need to issue like a query, or I need to like, hey, give me, I don't know, the top performing customers, like give me the, I don't know, the most queried actor or whatever the case. Like, how does the query happen if I have like all of these little units that just spread across the world and I don't know where they are?
That's a great question. So in terms of Akka.NET persistence at a very small scale is about giving individual actors the ability to become reentrant, is really at its simplest state what it's all about. Where if I have an actor that, imagine I have my big cluster up and running and I go and kill one process that had thousands of actors running on it. I need some way for those actors to recover their previous state. That's at its simplest form what Akka.NET persistence is really all about. However, taking a step back and say, okay, well, that's great for individual actors, but I've got a business to run and I need a bigger picture look at all the things that system's doing. How do I stay on top of that? Well, we've got a couple ways of doing it. Probably the most popular technique people use in combination with Akka.NET persistence is CQRS, where they'll basically subscribe to all the events actors are persisting. And I'll show you an example of how you can do that. If I go to my code sample I demoed a little bit earlier, I have this product index actor. This actor is created as what's called a cluster singleton, meaning there's exactly one of these in the entire cluster. So when everyone wants to talk to the singleton, they use what's called a cluster singleton proxy, which is basically a router that knows where to find this actor in the cluster and will direct all of its message traffic to it. You want to use a cluster singleton for workloads that can't be very easily parallelized. Job schedulers, work trackers, and in this case, an actor that just owns an index. Those are all things that are best done kind of inside a singleton. The way this actor works, if I scroll down here, this is what's called the pre-start routine inside an actor. This is a piece of code that runs before the actor processes its first message. And each time an actor restarts, whether it's being killed or recreated, or whether it's recovering from an exception, this code will always run. So what I'm doing here is getting a hold of what's called the read journal, which is a way of being able to essentially listen for all the events that are being written by actors to their Akka.NET persistence data store. In this case, it's SQL Server. And so I'm going to say, I want to get a list of all the persistence IDs, and I'm going to filter for persistence IDs that begin with this constant here, which is totals, meaning this is, if I have many different entities all running to the same journal, I only want to listen to these ones. And then for each one of those, I'm going to go ahead and create a new product found entry for this product ID. And I'm going to send a copy of that message to myself here. This is using what's called Akka streams. This query is running continuously behind the scenes. So at a rate of about once per second, we go ahead and run a constant time query to see if there's new data. And if there isn't any, the stream doesn't run. If there is data, we retrieve it. And then these little link statements execute after that is what happens. And so we're able to go ahead and essentially use this to create secondary indexes if we want to, or we can go ahead and create a materialized view. So we have some customers that have on the order of billions of events that are stored in Akka.NET persistence, probably even higher than that if I really go looking for it, maybe on the order of trillions potentially. And what they would use in order to get some business intelligence around that is they would take these events as they're being written and materialize them into indices for business analysts, is what they would ultimately do. The raw event payloads that are stored in AkkaNET persistence are really designed to make actor recovery simple. They're not designed for someone to run a large SQL Server analysis services job against. They're not really built for that. So in order to get it built for that, you want to go ahead and repurpose that data and translate it into some form that can be more easily queryable along those dimensions. And that's what AkkaNET persistence query does very well. So a lot of customers use this for that purpose. Now, the other ways you can run queries against actors is by actually messaging the actors themselves, if you really wanted to, which is what we do up here. Whenever we find one of these new product actors, we actually go and query the shard region actor. Basically, the way we go and create actors on demand inside a big cluster is we use a technology called AkkaNET cluster sharding, which will create for every single unique ID that's found inside any of the messages the sharding system can handle, we instantiate a brand new actor somewhere inside the cluster. This is very similar to the Orleans model, is what it is, for how we do this. And so we're basically interfacing with that shard region right here. And that shard region is programmed. If I go and pull up my infrastructure for this right here, this piece of code right here is what determines what the unique entity ID is for each message that goes through this router. And so in this case, we're looking for a marker interface that includes a unique product identifier. And all the messages for the same product identifier all go to the same actor. And there's guaranteed to be exactly one of those for each unique identity inside the network at any given time. And we even guarantee that when there's network splits or there's outages inside the network, we're able to go ahead and essentially guarantee that there's going to be at most one copy of an actor anywhere in the network at any given time for each particular unique identity. And so in this case here, we're actually going in sending this fetch product message to that actor, and we're getting back this fetch result down here, which we're using to go ahead and get some display data. Because right now, the only thing we get out of AkkaNET persistence query is the unique ID. We're getting the display information about what that ID means right here, this product found data. So we're actually querying the individual actors for that. So it could be through a combination of different tools, but generally speaking, those are the approaches people use to try to take that actor data and make it surfaceable for things like business analysis later.
So I guess from that perspective, if I know I'm going to run certain types of reports or process the data in a certain way, it's like I have to think about those projections inside of my actor and kind of build it into it. Because the other side would be, as .NET developers typically do, like everything's stored in SQL, and so I could just look at a database, right? And I might not know what the query I'm going to write, but I could kind of like play around with the data and get it. But because the actor persistence mechanism isn't designed for that, it's like, okay, I have to think about the types of queries that I want to do and the way that I kind of want to project this information. And then now within my actor methods, within receive or command or whatever the case is, start to like build some of that intelligence into it, right?
Yeah, you want to find ways of discovering the events you need to build reports, basically. And the other sort of approach for that I'm not really showing here is you can add what's called a tag to an event, which is basically a secondary index. You could do that if you want to. That makes it easier to find like-kinded events across multiple entities that way. So a good example, if I tagged every single purchase as a purchase event, I could go ahead and just search for those and not have to go query every entity in my system if I want to. The other approach people use, and this is particularly true for people who are porting legacy applications to Akka.NET, is you can just reuse SQL queries directly inside your actors if you want. There's nothing stopping you from basically injecting a entity framework DB context into an actor and running a query that way if you wanted to. That's totally doable as well. What AkkaNET persistence is designed to do is make there's some life cycle stuff that goes into the calculation of how an actor recovers its state. Namely, in order for this actor to be consistent from a data perspective, we need to guarantee it's recovered everything from its previous state before it begins processing any messages. And that requires a very powerful feature of Akka.NET called behavior switching, which is basically the way actors can change how they process messages while they're processing them. It's what's necessary for modeling things like state machines in Akka.NET. Let's see if I have an example of one, actually.
So it's kind of like if you're thinking about workflows, right? Like if I had a multi-step workflow, when I get the message the first time, behave this way, and then any subsequent messages I want to go down like a different path, right? Based on like whatever the concept of that is.
You'd use behavior switching for modeling workflows. You would go, and let's say if you have an event that arrives out of order, let's say you have multiple parallel activities as part of a workflow that are happening at once, but you have to have piece of data A first before B and C can be successfully purposed. Yep. Well, if you get B first, you could just stick it in what's called the stash inside an actor. In fact, I'm going to go ahead and modify my code sample here a bit. I'll go ahead and do I with stash. Go ahead and implement that. And then I'll go ahead and create let's see. This is my product index actor, which I guess I'll go ahead and create new behavior here. So I'll go ahead and take, let's see, product found and fetch result. Okay, so let me go ahead and actually create another one, waiting for data. Ready? Let's say here's an example of a little race condition that this actor might potentially have. What if I receive a product found, but before I get my fetch result back, I get a fetch all products message, meaning that I'm going to be missing display data for at least one element inside my system, right? So if I want to go ahead and try to fix that, what I might go ahead and do is move my product found event into here, and I might move my fetch result event into here, and I'll go ahead and move my fetch all products into here. Then I'll go ahead and have my done down here as well. I'm going to have this actor begin in a ready state, and I'll go ahead and trim some of my white space here. Then when I receive this product found message, I'll go ahead and call context.become. We'll do waiting for data. Actually, I guess it's just become waiting for data, isn't it? Yeah, there you go. Okay, good. Waiting for data. And then down here, I'll do a receive any, which is a catch-all. Actually, I'll do stash. Oh. Once we get fetch result, we update our data. I'll go ahead and call become ready. Then I'll call stash.unstash all. What I just did here is I actually changed the way this actor is processing messages a bit. As soon as I receive this product found message, I need to go and query my shard region to get this fetch result data back, the display information I need as part of my index. What I'm doing is basically saying that if I get this message, but I haven't received this one, then I can't process my fetch all products message right away. I have to switch behaviors and wait for this fetch result to come back. And once that happens, I can go ahead and basically shift back to my previous behavior and dump all the messages that were in my buffer, this little stash I created down here. I can basically dump those messages back into the front of my mailbox and begin processing those again. So this is how I just created like a little state machine in order to solve this type of external race condition that could happen in theory, because I've got multiple asynchronous things happening. That's an example of one of the things that AkkaNET Persistence does for you when we're recovering data. If you were using, let's say, a DB context semantic framework, you would have to basically orchestrate that yourself, which, as I just showed you, isn't terribly complicated. But these are the sorts of problems from an infrastructure standpoint you do have to reason about.
That makes sense.
Does that make sense?
Yeah, that makes sense. So I'm wondering too now, since you said that we can do these workflow type patterns inside of Akka, like when inside of my receive handler, I'm guessing we call them handlers, is there like a timeout there since actors are serial? Like what happens if it takes too long to return? Like is it going to like freak out, or is it just going to activate another actor that's not busy to like process the next message?
So by default, if the actor blocks and deadlocks, it'll tie up the thread and it's not going to do anything out of the gate. Akka.NET is very unopinionated. Just like how the .NET thread pool is. If you tie up that thread, the .NET thread pool will inject additional threads now in .NET 6. But that thread that you were blocking is still stuck there, right? Unless something comes along and reaps it. With AkkaNET actors, if you have, let's say, an async await block in there, you'd want to make sure you use cancellation tokens inside of it, which is, by the way, these can be changed to receive async. I could turn this into async method handler here if I wanted to. And if I wanted to do I don't know, await task.delay, or let's do 100 milliseconds here. That would run no problem. In fact, let me, just to make this a little bit clearer, I'll go ahead and move that up here. So what you'd want to do to make sure that this actor is able to free itself and keep processing messages is you'd want to include, obviously this isn't going to deadlock, a task.delay isn't, unless, I don't know, the CPU is totally pegged, in which case it's kind of pointless anyway. But you'd want to go ahead and pass in a cancellation token inside of here as a best practice.
Okay.
So for really long running processes, what developers will typically do if they're being managed by an actor is they'll go ahead and kick that process off and have it execute outside the actor's context. They'll have the actor behavior switch and hold on to either a cancellation token or some other resource they can use to abruptly cancel that task. We have a lot of customers that do things like big ETL systems where they're scanning for data on, let's say, like, good example, we have a lot of customers in the security industry that are doing things like scanning a tenant's Active Directory structure, or they're scanning their SharePoint for files that violate some rule. And those are cases where they have these super long running jobs that hundreds of actors are working on. They need the ability to shut all of them down at once. Another example of that is we have customers in banking that do things like asset line management, where they're importing tens of millions of individual mortgage data bits to go ahead and do a broad comparison in terms of how is this portfolio of mortgages performing versus last month, that sort of thing. I saw a question from Jose Silva come up a minute ago about how does Akka.NET schedule itself using coroutines. Is that what? Did you put that question back up on screen again?
Yeah. He wanted to know more about what's the magic under the hood. So like, how does the messaging and the processes work?
It's called the dispatcher is what it is. And basically it is a set of, long story short, it's a fair scheduling algorithm that is and by the way, it's also configurable. We have different types of dispatchers in Akka.NET. So for instance, our people who are building a WPF apps or MAUI apps can actually use what's called a synchronized context dispatcher, which allows an Akka.NET actor to run on the UI thread of those applications. So you can actually have a message arrive over the network, and that actor can use that to go and update, let's say, a chart that's on screen inside a MAUI app. And you can do that without any marshaling. It's already handled as a result of the way the actor's threading model works. But by default, all actors run on the default .NET thread pool. And when an actor gets sent a message, it gets scheduled by the dispatcher. And the dispatcher has a number of different threads that service it, basically. They go and check the dispatcher for work. Each dispatcher work item has a queue of actors that are all ready to process messages. That actor is allowed to process a burst of up to 30 messages before it has to yield control to the next actor behind it. It works very similarly to, let's say, an operating system thread scheduler. Looks like we lost Cecil there.
There was something with his audio going on.
It sounded like there was something going on right outside his office.
Maybe it's like Scott that gets the radio on his mic. Maybe he's catching some radio.
Yeah.
Aaron, so Aaron, we're getting close to the close of the hour, and I am going to give you a chance to summarize and point people to GitHub or whatever. But before we do, and I realize that this is a very loaded topic, so just like from a like 30,000 foot view, we had a whole bunch of questions. I'll just highlight the one that was kind of the most detailed there. So there's a lot of actor model frameworks out there. What makes Akka different?
What makes Akka different? Boy, okay. Give me 2 minutes to answer a question I could spend 2 hours on.
Yeah, and I realize that's probably not.
We might have to have you back for a second show.
That's fine with me. Okay, the short version of why I use Akka.NET. Philosophically, and I say this with all the love in the world as a former Microsoft employee myself, Akka.NET's philosophy is quite different from Microsoft's philosophy when it comes to tool design. The philosophy behind Microsoft's tooling is by and large to abstract away infrastructure concerns so you can focus on basic business application development is what it is. That's true throughout a lot of their Azure products, throughout individual, let's say, technologies like Entity Framework and so on. And there's a lot of merit to that. Orleans and the other technologies you mentioned follow a very similar methodology to that, where they are designed to go ahead and abstract away infrastructure concerns and let you focus on business concerns. The downside of those approaches tends to be that at a certain point when your application is large enough, now you have to know how that magic works. This is true whether you're doing performance tuning in an Entity Framework or trying to understand why an Orleans virtual actor is performing like XYZ. AkkaNet's philosophy is somewhat 180 degrees backwards from that, which is we give you a lot of fine-grained control over how things work through a basically infrastructure that has a fairly small number of moving parts by contrast. So it's fair. It tries to be unopinionated in the sense of magic is something you have to opt into explicitly in Akka.net, whereas with a technology like Orleans, it's something you have to opt out from. Good example. When I call actor of, when I'm starting an actor, I know that actor is going to be instantiated locally in the process I am in right now. And that's just how it works, whether you're clustered or whether you're working remotely. With Orleans, let's say a grain allocation, it's somewhat arbitrary whether they can be allocated. However, if you do need to start co-locating certain grains to work together, now you have to go customize your own grain placement algorithm to go and do that. Whereas with Akka.net, it's something that kind of always implicitly worked and this very localized sort of low moving part way. That's an example of some philosophical differences there. The impact of them is that with Akka.net, you have what I call a downhill performance model where we give you the simplest but fastest possible experience out of the gate, and you systematically trade away some of that speed in exchange for other things that are more important to you. A good example of that might be data consistency or message deliverability might be another example of that. And so all the trade-offs essentially go in the same direction with Akka.net. With a technology like Orleans, it's more of a zigzag where you might go ahead and have something that's fairly simple, but out of the gate, but it has a lot of magic you don't know about. But as your application gets bigger and more used, you have to start learning how it works and learning what its constraints are. And that's not something you necessarily have to price in up front the way you do with Akka.net. The other thing I'd mention is in terms of the maturity and stability of the technologies, we get a lot, just to be blunt for a minute, Akka.net catches heat because we're a port of a Java technology, or really it's Scala. And we get, I think, unfairly dinged for that. And one of the questions I've been asked, as though it's like an intellectual, let's say, impediment of ours, is why don't you guys go and do your own thing? And I'm always puzzled by that because I'm ultimately a pragmatist when it comes to the design of our tools. And it's like, okay, well, Akka is a technology that powers large portions of Twitter, LinkedIn, Walmart, Amazon's own systems. It's been powering other large distributed systems technologies like Spark, for instance. Why on earth would I take all of that codified knowledge that's available in open source space and deviate from that for the sake of saying that I'm doing something original? These are designs that are battle proven in ways very few .NET technologies ever are. And that's one of the reasons why we started the port in the first place, was not because we sought to create an open source business, but actually because at my marketing automation company I started before Petabridge, I absolutely needed a low latency distributed systems experience in order to successfully save my business, is why I did it. It was so ultimately these decisions are pragmatic. All the Akka designs are, by and large, very battle tested and have evolved over time to go and accommodate changes in the ecosystem. Now, that's not to say technologies like Dapper or Orleans aren't battle tested either, but Akka's been around longer. It's able to scale up and down a lot better than those technologies are. In particular, the scaling down part. You can't really run Orleans on a WPF application. You can put an Orleans client on there, but you can't go ahead and host a full actor system the way you can with Akka.net. And so there's different trade-offs here in terms of the learning curve. I would say the one part is with Akka.net, the conceptual overhead will be higher, but you're able to bite it off in smaller chunks because it scales down better. With Orleans, you're building a distributed system from day one, but you're not going to have to learn as many new programming concepts as you would with Akka.net. So ultimately, I'm a fan of I'm a CTO first, not as far as the hats I wear. Even though I'm also the CEO of Petabridge, but I'm a CTO first. And one of the things I value most is having options in an ecosystem. And I think it's good to have them. And that's also, Microsoft obviously agrees. Otherwise, they wouldn't have me on the show, right? So yeah, having options is a good thing. We should celebrate that.
Yeah.
Agreed. So on that note, we're to the end of our hour. Can you send us? Is there a website or something where folks can find out more about Akka.net?
Yeah, absolutely. First thing I'll go ahead and link you to is the main Akka.net documentation. The second one I'll pull up is our Akka.net bootcamp. Let me just grab that real quick.
Okay, and I'm gonna throw that up on the screen there for folks. The Akka.net, and then the I'll throw up the Petabridge link real quick for folks.
Yeah.
There's the boot camp, and I have get this. I found the script. So thank you everyone for watching.
I just realized I never ran my Kubernetes cluster, even though it's already up behind the scenes here.
Oh,
but
no,
we'll have to save it for an episode 2 sometime.
You know, you certainly have a great breadth of knowledge on this topic. We'd love to have you back. So thank you everyone for watching on .NET Live. I want to thank our guest Aaron Stannard, and I want to thank Cecil Phillip for coming back to host with us this week. Want to thank my co-host Myra Wenzel. Check out our other great .NET Live TV streams and videos at .net/live, and tune in next week when we'll be talking about querying GraphQL with LINQ. Thank you everybody, and have a good week. Wow.